Okay, so we will start. So hello everybody, nice to meet you. So my name is Valérie Véniard and I'm working at the École Polytechnique close to Paris in the Laboratoire des Solides Irradiés. And the topic of today is, well, that's the first part of the nonlinear session, so it will be related to nonlinear optical spectroscopies. This is the outline. First, I will show you what kind of process we are looking at, some example of nonlinear spectroscopies. And in the second part, I will show you how we can calculate in an ab initio way some nonlinear response. And this will be, see if it works. Yeah, so second order response and the E-fish, which is a third order response. So some examples. So the idea is to know the response of a material. It can be a solid, it could be atoms or molecules, to an external perturbation. In our case, the external perturbation is an electric field because it's the response to some electromagnetic radiation because we are doing optics. And so we have an incoming external electric field, which interacts with the material, and we are looking at the response. The quantity that is interesting for us is the polarization of the medium. The external field inside the material will create a polarization, which depends on the frequency of the field, of the intensity of the field. And this polarization can be in the framework of low, well, not too high, let's say, not too high intensities, can be expanded in a series in terms of the electric field. So we have several terms. The first one is just proportional to the external field. We have a second one, which is proportional to the square. So that's the second order response. Then we have the third order response and so on. The idea of this nonlinear stuff is the fact that we can create new frequencies. And you can see this, so the external field is an oscillating function of time, so that is described here as a cosine. The frequency of the external field is omega. And if you plug this quantity into the polarization and linearize all the oscillating function, what you get at the end is a term that does not depend on time, which is proportional to the square of the amplitude of the electric field. Then a term that is proportional to the cosine of omega t. So omega t is the incoming, the omega is the incoming frequency. Then a term that depends on twice the incoming frequency and 3 times and so on. So the nonlinearity of the medium will create new frequencies because you have omega at the beginning, 2 omega, 3 omega, and so on at the end. So that's basically the idea of the nonlinear spectroscopy. In terms of the external field, well, the first term is just proportional. This term is just proportional to the external field, and when we add all the other terms, we are changing the dependence on the external field. So we can include only the quadratic terms, so the second order response, the cubic one, and they all have a different behavior in terms of the amplitude of the field, which will change the response. So the first one, linear optics, so proportional to the external field. The coefficient which is just in front is called the susceptibility. So we have the first order susceptibility, second order. And so this one has no change in the frequency. And all the others are considered as nonlinear optics. So that's starting at second order, and you can go as high as you want. So nonlinear optical spectroscopy was discovered, well, not discovered, but the experimental study of nonlinear spectroscopy started in 1960 with the discovery of the laser. In fact, it's quite obvious that if you go to higher terms, you need higher intensities. Otherwise, they are just too small to be detected compared to the linear terms. So with the laser, we can have enough intensity to so that all the higher order terms come into play in the polarization. So that's all these terms that can be detected. So just a short word about laser. So laser, which means light amplification by stimulated emission of radiation. There are several properties that are very important for us. So the high intensity, that's obvious, but the spatial coherence and the temporal coherence are very important, because that's the way we can get intense, highly collimated monochromatic beam. And that's what we are looking for with the nonlinear optics. So for the collimated beam, if you just take an ordinary source, just the lamp, I mean, you get light in whole space. The emission is more or less isotropic. The fact that we have a laser will allow us to have very tiny collimated beam that propagates on a long distance without defocusing. And we can also collimate the beam on a very tiny spot, which gives access also to spatially resolved spectroscopy. So that's one point. Then monochromaticity. So this is again some examples of light that do not come from laser, so just the normal lamp. And this is the intensity as a function of the frequency of the emitted light. So you see that we have a huge band of frequencies that are emitted. It can be a little bit better if we have some tube, neon tube, for instance. So you see that the range is a bit more narrow in that case. For a laser, that's what we get. So just one frequency which is emitted. So we have different laser. We have blue light, red light, but it's in principle always monochromatic. This is a bit theoretical, because in fact, we have the first intensity relation of Heisenberg, which couples the duration of emission to the wavelength, that the delta wavelengths that are emitted. And the shorter the emission is, the broader the range of wavelengths you get. And for instance, this is the theoretical spectrum of the laser, so a kind of delta peak. And depending on the duration of emission, so it can be in the picosecond range, it can be in the femtosecond range, then you will get a broad spectrum. If you go to attosecond pulses, you get something which is becoming very large. So that's what you get, in fact, in real life. You have a quite important range. It's not completely monochromatic. So the first nonlinear process, that's second harmonic generation. First of all, it's the first of the nonlinear case, the first one which does not fall into the linear optics. And it does not require a too high intensity. So it was discovered in 1961 by Franken and collaborators. And this is a schematic view of the experiment. Just to explain how it worked at that time, in fact, they did not notice at the beginning that they got second harmonic generation. It was such a tiny spot that they thought it was just something wrong in the experiment. They did not notice that it was really part of the spectrum. It's just after seeing that the position of this strange spot was corresponding just at the second harmonic that they realized that they got it, the second harmonic was discovered for the first time. And so that's how the spectrum looks like. So here you have the incoming frequency, and here you have the second harmonic. So you see that if you look at the spots of the incoming frequency, you need really good glasses to see the second harmonic point. You really have to think it.
I look at the PDF, for me it's white there.
It's just white, yeah. In fact, it was just a small...
Because you don't have the good glasses.
You could think that it's a piece of dust on the... No, finally it was second harmonic generation. Yeah.
Just quick, quartz is centrosymmetric?
Depends on the, you have several prototype of quartz. Yes.
Okay.
The normal one, yeah, is some crystallographic are centrosymmetric, but not all of them.
Okay, so not this one.
Obviously not this one. So what is second harmonic? So you have a nonlinear medium, an incoming frequency, and if you look at the output, of course, you have the incoming frequency that is transmitted through the medium, and the second harmonic. So the second harmonic corresponds to a process in which two incoming photons are absorbed by the material, and one photon is emitted. And due to energy conservation, the energy of the emitted photon is twice the energy of the incoming photon. Now, in terms of amplitude, if we look at the expansion in terms of the electric field, because the intensity is not too high, so all the terms in the expansion are decreasing. And we have the linear term, which is much larger than the second one. So second harmonic generation or second order response, which is also much larger than the third order response. And it goes like this. But we have to take into account the symmetry of the material. And the chi2 in the dipole approximation, so in the range of long wavelength, the chi2 is equal to 0 for centrosymmetric materials. And in fact, it is also true for all even terms. Chi4, chi6 are always 0 for centrosymmetric material. So in that case, you go directly from the linear term to the third order response, the chi2 disappears. Second harmonic generation is not the only process that you can get in the second order response. It's the one you get when you have only one incoming field, so only one frequency which comes into play. But if you can imagine that you have two incoming field with two different frequencies. So one is omega-1 and one is omega-2. And the second order polarization will contain all these terms. So second harmonic of omega-1, second harmonic of omega-2. So the first one depends on the square of E1, the amplitude of the first field. This one will be proportional to the square of E2. And then you have cross terms. You can have some frequencies generation. So in the process, one photon is absorbed at omega-1, one photon is absorbed at omega-2, or the other way, of course, it's symmetric. And the photon that is emitted is omega-1 plus omega-2. And the same for the difference between, because you have plus omega and minus omega. Just imagine that you represent your electric field as a cosine. The cosine is a sum of two terms, the frequency plus omega and the frequency minus omega, which allows the fact that we can have omega-1 minus omega-2. And this is difference frequency generation, which is widely used because it's a way to get some microwave, so very low energy in a range where we cannot have lasers because lasers are not available for all frequencies. Okay, so that's typically what we have. In the case of the linear response, we have one peak at, if we look at the field in terms of the frequency, we have one peak at omega-1, one peak at omega-2. But at second order, we have a peak at 2 omega-1, 2 omega-2, one in between, which is the sum of omega-1 and omega-2, and one at small frequency, low frequency, which is omega-1 minus omega-2. There is also another case where we get a static field, because we can have, if you have only one field, you have omega minus omega, and it's a way to get a static response, because from an oscillating field, you get something that does not depend on time anymore, because the frequency is 0. So that's called optical rectification, but I will not go further on that. So that's the graphic for all this process. So some frequency generation is very close to what you have seen already with the second harmonic generation. And here it's a small frequency that is emitted. If you have questions, no.
What is the prevalence of each of these some frequency generations or second harmonics? Because they all happen at the same time?
Yes.
But some might be more probable than others? Does it depend on the material?
Well, it will depend on the material, of course, because the coefficient that you have, the chi2, it depends strongly on the material. So it depends also on the frequency that you plug. I will show you later the chi2, what it looks like. But it depends on the material. It depends on the frequency, on the incoming frequency, and also on the outgoing frequency. So even with two different fields, omega-1 and omega-2, the response will depend on what you're looking at. Or you're looking at omega-1 plus omega-2, omega-1 minus omega-2 that enters into the response. So this depends. In principle, you do not get orders of magnitude between these steps, except if you have a resonant process. Because I will show you later, but in the expression of the chi2, you have denominators that contains the difference between two eigenenergy of the material minus a frequency. If the frequency match one difference between these materials in the eigenstates, the process is becoming resonant, so very hard. And of course, depending on the fact that you have omega-1 plus omega-2 or omega-1 minus omega-2, it can be resonant or non-resonant. And then you can have a big enhancement or decrease of the response. So that I would say that it's mainly the fact that it is resonant or not that will cause the highest difference between the processes. This. But what I will show you I will show you a chi2, a real chi2, what it looks like.
Okay.
Okay, so there is another second order non-linearities, which is non-linearity with a static field. So it's a non-linear process because it depends on two fields, but this one was discovered much before second harmonic generation. So it's called electro-optic effect. It's the fact that an optical property can be modified if a static field is around the material. And this is what, so it's, yeah. So you have an incoming light as before, and the electric field that modifies the property. And this, in fact, can be also described as a second order response because a static field can be considered as a field at frequency 0. And so it's a photon with a frequency and energy that is equal to 0. And so if you want to describe this process, you have a chi2 that is the frequency of the incoming field, 0, and the outgoing frequency is the same as the incoming one. So that's a second order process that does not modify the frequency of the emitted light, but can strongly modify the intensity of the response. So why are we so interested in the second harmonic generation? The first reason is the fact that it can be used as a probe for materials. I told you that second harmonic generation is only non-zero if the material is non-central symmetric. So it means that in fact second harmonic generation or chi2 processes are strongly sensitive to all the symmetries of the material. So if you have defects, if you have a surface, you can have different type of response. And also it will give access to other states that you cannot probe with the linear optics because you absorb 2 photons. And so you get higher in energy and you also have access to different angular momentum because absorbing a photon will change the angular momentum of a state. And so you have access to other states that you cannot see with just linear optics. So it is widely used for the analysis of surfaces because a surface is the strongest breaking of symmetry. I mean, you have a surface, below you have the material, above you have the vacuum. So whatever the material, you have a response at the surface, even if the material is centrosymmetric. It's just the fact that you have a surface that breaks symmetry. In the same way, thin films, because in that case, you have 2 surfaces. You break the symmetry, interfaces, nanowires have been studied with the structure of these nanowires have been studied with second harmonic generation. So that's just schematic view. So chirality in molecules can be studied, surface reconstruction, because at the surface it's quite difficult to know how the atoms are organized at the surface. So second harmonic is used for that. And also in biology, collagen has been studied using second harmonic spectroscopies. Then a second application is the development of and the characterization of new materials to get new optical devices. For instance, if you want to build a laser, you need nonlinear medium. And there is an important search for efficient nonlinear medium and mainly also for second harmonic generation, because they have to be efficient. For instance, if you have a pointer, a green pointer, usually it's based on second harmonic generation from the red light, because if you multiply the frequency of the red light, you get a green light, and there is no laser in the green range. Well, it's coming. And it is also used, as I told you before, in the microwave regime, where you cannot, because lasers are built on atomic transition between states. So what you get is what nature gives you with atoms. You cannot have all the emission. And it's difficult to have emission in the microwave regime. So this is based on on frequency different process where you just subtract 2 frequencies and you get something which is very low. So, and we have to search for these new material that are efficient, because of course a second order process has a low probability to occur. So we need efficient stuff. There is also a possibility to use second harmonic generation it would be very interesting to design some silicon photonics. The problem is that silicon is a central symmetric material. So if you want to use silicon, you have to go to third order process. So you need high intensity, and the effect would be to just destroy the material, because if you use a too high intensity on a solid, you just make holes in the solid. So it's not. So the idea is, could we have in some way a second harmonic with silicon? That would be very important for photonic industry. And one possibility is to break by hand the central symmetry of silicon by applying some strain on the material. Silicon becomes non-central symmetric, in that case, depending, of course, on the way we apply the strain, and it becomes an emitter for second harmonic generation. So that's depending on the percentage of strain. That's the result of an experimental, and we did some calculations which were quite good agreement. And depending on the strain, we can have an emission of second harmonic generation with silicon. And finally, if we go to time results spectroscopy, which is very up to date now, it's a way to probe ultra-fast transitions in solids. I just give you two examples. This one is the ultra-fast demagnetization in chromium oxide. So it's usually based on bond probe experiment, where the material is excited by a strong pulse, and a probe comes to probe the change in the material. So it's a short pulse, and by changing the delay between the pump and the probe, you can see the way the system is evolving into time. So this one was the demagnetization in chromium oxide. So you see that we have a strong demagnetization, and then it goes back to the ground state. The order is picosecond. And this one was an ultra-fast reversal in the ferroelectric polarization. So that's the same idea. You perturb the system, and then you follow in time with second harmonic, which is quite sensitive to the what happens into the material as a function of time. Of course, this means that we have short pulses if we want to follow processes that are in the picosecond or femtosecond region. Femtosecond is 10 to the minus 15 seconds, so that's quite short. So let's go now to third nonlinearities. So that will be quite short. It's the same idea. So we have second harmonic, so we can have third harmonic. We have some frequencies, so we have the three frequencies that we can add. So we had a lot of processes that can occur. And so the simplest one is third harmonic generation. You absorb the 3 photons, and the emitted frequency is 3 times the incoming one. This one is a bit different. It's in a third order process. So I said you can absorb 3 photons, but you can also have emission. So you can absorb 1 photon, emit the same, we absorb the same. That's a 3 photon process. And then so it's the same frequency as the incoming light, because 1 plus 1 minus 1 plus 1, that gives you as the same as linear optic, where you have absorption of a process. So it will enter the expression of the refraction index of the material. But now it's an intensity-dependent term, and it's called the optical Kerr effect. So the refraction index is the one you get normally just by linear optics, and you have this additional term which depends on the chi3 in that case, and is proportional to the intensity of the field, so the square of the field. And it's, so there is no change in the frequency, but it is very important because this term acts as a positive lens. It means that it's a self-focusing term. And people doing experiments with very intense laser field are always very careful to this term because you have an intense light at the beginning. If at some point there is a self-focusing process that occurs in a lens, for instance, suddenly the intensity of the field is rising, and this can be very important, and you just break all your optical devices. So this is very fun. This is not wanted. I mean, people try to avoid this self-focusing term, but people have to be aware that it can be very important. So it's a Chi3. So I will not go to 4. We will count as 1, 2, 3 a lot directly. And then we have high harmonic generation. So at the beginning, the experiment was done on a gas jet, so noble rare gases. The principle is the principle is very simple. You have an atomic jet, an intense laser. In that case, it has to be quite intense, not really intense. And as an output, you have all kinds of frequencies that are emitted. If it's an atomic gas jet, in principle, it's a centrosymmetric material, so all the even orders are not present. So we have 1, 3, 5. It was measured above 400 harmonic. And what we get as a nice spectrum is this one. So it's all the lines here. It's in terms of the wavelengths. That's why they are not equally spaced. It's equally spaced if you look in frequencies, not equally spaced if you look in wavelengths. You have all these lines corresponds to emitted frequency. And the amplitude of the emission has a very typical shape. It's this one where for low harmonics, you have a strong decrease at the beginning. Then you have a plateau where all the harmonics are emitted with more or less the same frequency. And then you have a cutoff, and that's the end of the spectrum. And the position of the cutoff depends on the intensity and on the frequency of the input field. So this became, so it's, now you all know what we can do with high harmonic generation due to the last Nobel Prize in 2023 by Pierre Agostini, Ferenc Gross, and Anne Leyer, where they obtained the emission of attosecond pulses with this high harmonic generation. So the first pulse that was measured, well, not measured, but deduced from the measurement was 250 attoseconds. So just to be clear, an attosecond is 10 to the minus 18 seconds. So it's really the time scale of electronic processes in matter. And so this was the emission, the spectrum that was in time that was get from the experiment that led to the Nobel Prize.
I have a question concerning the previous slide. Why is the probability that frequencies within the plateau why is the probability that a photon can excite, say, a state that is higher, the same than previous states? Why do we have that?
In fact, you really you have to not to think in terms of the schematic view I showed you for the second harmonic, where you have 2 photons that are absorbed, one is emitted. This is well, not valid, but it explains well the beginning of the spectrum, where we have these 3 photons absorbed, one is emitted, 5. then it's something different that occurs. You have the light, so there is an oscillating electric field. The electrons are moving with the field because it's just the classical force. You submit a charge to an oscillating force, and charge is starts to oscillate. And because the intensity of the light is quite high, the electronic motion, the electrons go very far. But when the field is changing sign, the electrons are coming back. And when they are close to the parent ion, they can recombine. And this creates the plateau. And in the probability of having this, the emission does not depend that much on the energy of the emitted photon. But they are going, it's what is called the three-step model. An electron is escaping the atom by tunneling, goes away, comes back, recombine. And this gives rise to the plateau. And the cutoff, in fact, the excursion of the electron depends on the intensity of the field. And so after some time, they cannot go further because they're coming back. That's the maximum excursion they have. And the energies that correspond to this longer excursion cannot be reached. And so that's the cutoff, which is quite sharp. So that's why there is this, it's really the nonlinear process in a sense that you cannot anymore explain the response in terms of electric field. The series is not converging. So you cannot see, we have the second order process, the third, and so on. Okay. So now that you know almost everything on what we can do with nonlinear optics, how we can do it from the theoretical point of view. So there are several methods to describe the nonlinear response. So we have the perturbative expansion and non-perturbative expansion. So the difference between the two are, in one case, we have perturbation theory, and we take one term, the second order or the third order. In the non-perturbative expansion, you start directly with the full response. You do not expand it. So this one is mainly based on explicit time propagation, and Claudio will tell you more about that after the break. And I will just show you some example of perturbative expansion. We can use TDDFT. There are some finite difference methods. One is implemented into the ALINIT code. The Sternheimer equation can also be used to get a nonlinear response. And there are some calculations using the Bethe-Salpeter equation that you will see, I think, on Friday. That has been extended to second order processes.
Excuse me, when you say Sternheimer equations, you mean it's the functional perturbation here?
No, not necessarily. No, it's just it's a way to get to expand in terms of orbitals to certain order, and then you get the response to higher order. For instance, if you expand to order n, you get the response to order 2n plus 1. So it has been used a lot for the static response, but there are some cases where it has been extended to frequency depending. So what I will show you here is the second order time-dependent density functional theory approach. So this you probably know already. So the macroscopic polarization of the medium is, for this you need the displacement vector, which contains the total field, and this quantity, which is the macroscopic dielectric tensor of the medium. And this tensor this dielectric response is obtained in terms of the chi1, the first order response function that you probably already calculated yesterday, maybe. Was it chi1? Yeah. So with dp, that's what you get. So it's the same idea for the second order response. Then the displacement vector contains an additional term, which is the second order macroscopic polarization. And this second order polarization is described by a chi2 and the square of the total field. So the idea is to calculate this chi2, which depends on omega-1 and omega-2. We have some strange notations with the chi2, and don't be puzzled by this minus. It's just a way to write the chi2. So when you have a plus, it's the absorption of a photon, and when you have the minus, it's the emission of a photon. So in this chi2, we have the two incoming field, omega-1, omega-2, that are absorbed. And here it's minus omega-1, minus omega-2. So it means that we have a process in which we have the emission of omega-1 plus omega-2. It's a bit puzzling at the beginning, but it helps to see which type of process we are looking at. So what is the response function? The linear case, it is the functional derivative of the density in TD-DFT with respect to the external potential. And the dielectric response is obtained in terms of this chi, which for convenience is called rho. So it's a density response. So we look at the variation of the density with respect to a potential. So it's a density response function. And for second order, we have a density response function. And so it's the second derivative of the density with respect to the two external potential. You're still with me? And once we have obtained this second order density response function, we have the macroscopic response function. That's the equivalent of this quantity, but to second order. And in that case, you see that it depends also on linear terms. So this one is only the second order, so the second order response, and it is multiplied by 3 dielectric response, one at the two incoming frequency and one at the outgoing frequency. So that's what we have to calculate at the end. Same as yesterday, we have the independent particle response function, what is the Kuhn-Sham response function, and we have a Dyson equation to solve to get the full response function, so the chi1. Chi01 for the Kuhn-Sham response function. The equation depends on the Coulomb potential and on an exchange correlation potential kernel that has to be approximated. Back to basics. So this is the new Dyson equation. So we have the chi2, the chi02, which is the Kuhn-Sham response function. You see that this term is very similar to the linear case, except that it is squared now, because we have two interactions. So the fxc, which is here, and we have this additional term, gxc. And gxc is the second derivative, functional derivative of vxc, the exchange correlation potential from DFT, with respect to two densities. For this term, we have no approximation. There is no So for the moment, in all the calculations that are done in this framework, this kernel is set equal to 0. We have in mind that it's a small correction. For some calculations, it's clear that it is very small because it corresponds quite nicely with the experimental results. It might be non-zero for many cases, but for the moment, there is no approximation that are available for this term.
So once you ignore this part and consider FXC to be substituted by RPA, so basically we have the response of the system to the first. Yeah, in first order, we have the response of the system with respect to Coulomb, and the second one is the response of the third order to Coulomb again.
Yes. You mean here
in the first
you have exactly the same
Like
level of
Dyson orbital,
approximation.
the
Yeah.
response.
Yeah, you have, if you set, okay, so we suppress this term.
Yeah.
We don't know what we can do with it. So if we suppress the FXC here and here, it's the RPA result, the same level of approximation.
That's good.
And then you can include an FXC that is the best suited to the material. So that's exactly the same way of going into the level of approximation.
Okay, I understand. In first order, the kernel is RPA and is Coulomb V.
Yes.
And this for second order, what's the kernel? I couldn't actually realize.
Well, you have this, and this one is the same as the linear case. It appears exactly in the same way.
The same kernel.
It's the same kernel. It's the same kernel here. So, of course, the validity of a kernel can depend on the order of the approximation. I mean, if you have a very good approximation for the linear case, you can expect that it's good for the second order case. There is no proof because it's not the same process. So an approximation is always valid in a certain framework. So you have to check. And so here it's a bit difficult to check whether it's good or not because there are not so many experimental results in terms of spectra. We have some static response for a lot of materials, but to get a full spectrum in terms of frequency, we don't have so many. So it's, I will show you results, but it's difficult to really carefully check with the experimental results. And to compare with other calculations, which do not depend on the kernel, that's the idea, to check whether the kernel we use is good or not. The only way is to rely on Bethe-Salpeter calculation, in which you do not have to guess any kernel. And Bethe-Salpeter to second order has been done, but it's quite heavy.
Are you gonna show Bethe-Salpeter notation for this second part? I mean, second order response or not?
Some results?
No, for Bethe-Salpeter form of this equation. Now it looks like
I think Claudio will show you something. Do you show something with the Bethe-Salpeter?
Yeah, show with Salpeter, but I don't think I will
Go to
have
second
time to go to second order.
Yeah, okay.
Maybe-
My question is that once we are gonna consider the first order, we have zeta and this kernel, and okay, somehow in terms of self-energy, it includes vertex and blah. What is the second order kernel? How it includes?
Well, it will. In fact, well, it depends what. How can I say? With the Bethe-Salpeter, we have second order, but in terms of the perturbation.
Yeah.
when you take the difference between the TDDFT or the beta salpeter is the treatment of the electronic correlation. So the kind of process that you put in the beta salpeter for the linear optic or the second order process, optical process, will be the same. You do not change the way you treat the electronic correlations by doing a linear optical calculation or nonlinear optical calculation. This is only on the order of the external perturbation, the electric field. And all the diagram that you include or not in the calculation,
Still exists.
they are still, well, if you have a beta salpeter calculation or not, it will be the same. The change is just on the way you treat the external field, the light.
Where can you confuse about the intensity approximation for the GXC?
So GXC, we know. Tu as parlé du long range kernel?
Oui.
So, for instance, there is a kernel that Valérie told you.
The long range
Yeah.
kernel.
The long range kernel.
The last kernel that you've shown.
So the shape of this kernel is a coefficient divided by q square. You can, if you plug a shape like this, a form like this for the GXC, just by considering that it has to be non-divergent when q goes to 0 and things like that, the structure has to be some beta parameter divided by q to the power 3. This is obvious, but there is no way to decide what is this beta parameter. The only way would be to compare to a beta salpeter calculation or to experimental results. And when we compare to experimental results, there is another approximation that is made in all the calculation, is the static approximation. All the kernels do not depend on the frequency. And it's difficult to approximate the beta, knowing that there is another approximation that is hidden in that. And so the values that we could get for beta by comparing with the experimental result might be completely meaningless, because we don't know what is more important, the static approximation that we do, or the fact that we neglect the GXC. So for the moment, it's that's all. That's the end of the story for the GXC.
But in ADA you get a constant, right? Still is
But well, the shape of this kernel, yes, the coefficient is supposed to be constant. Yeah, we made some tests. Did not work. I mean, we used, because it was quite easy to implement it and to say, okay, we decided a beta, but let's put 1, let's put 10, let's put 1.1, and we did not even know the sign. So it can be 1, it can be -1. So we made all these tests, and we never found a good result. Well, something that was improving the agreement with other theoretical calculation or experimental results. So for the moment, we try to improve the efficacy first, and then we will see later.
Within the context of head in pentagon, I guess this meaning of vertex is quite similar to this variation of exchange correlation with respect to density. Vertex is basically the variation of self-energy with respect to G, right?
Yes.
So, have you think on this, that this within
Well,
where this version might
In fact,
be helpful?
we use a little bit of this because we need some corrections for our energies. Because the DFT energies are not correct, and it's starting with the gap that is not. The expressions we have are taking into account the fact that we correct the energies. What we do in practice is we are not doing a full GW calculation on top of which we could build the Cauchy response function, but we use the scissor approximation. That's what we do. From all the calculations I did, it's a good approximation. As long as you do not go too high in terms of the bands, because then the scissor is a rigid shift of the conduction bands. But in the optical range, it's not bad. So, but we can also do the full GW calculation and correct all the energies. That's also a possibility. There were some calculations that have been done. For gallium arsenide, the difference was not was very small. In fact, the scissor approximation was enough. So, how do we do the ab initio calculation? So we start from the ground state, which is what we do is with ab init, and we have so at this point to decide with which VXC we are using. Then we have to evaluate the independent particle susceptibility, the one which is based on Cauchy orbitals. Then we solve the Dyson equation, and here choice of the kernel fxc gxc equals 0. And then once we have the susceptibility, we calculate the macroscopic susceptibility. And this is done in the code to light that you will use this afternoon. So what is a second order response in real life? So this is the independent particle approximation, so the Chi02. So it looks very complicated, but just to explain a little bit. So we have sum over bands. So we have 3 bands, because there is the first one, absorption of 1 photon, absorption of the second photon, and back to the first band. So that there is a sum over 3 bands and a sum over k points. We have for all, there are several terms, but we have 3 matrix elements at the numerator, the one which goes from the initial the valence band to another band, and three terms, and the final one goes back to the initial band. And we have 2 energy denominators, which depends on here energy difference of the material, frequency of the laser, and here another one, and this time it's 2 omega, so incoming frequency, outgoing frequency. So it is in this way that we can have an important change in terms of frequency, because if we have a resonance here, it means that we have 2 bands which energy corresponds exactly to the incoming frequency. You will see a peak in the spectrum. You can have also the case where it corresponds to twice the frequency. So that will give you also a peak in the spectrum. And you can have double resonance. It means that some bands are resonant with this term and some bands are resonant with this one. So you have a double resonance process. As soon as you have a double resonant process, you can have interference between them, and it's not always constructive interference. You can have destructive interference between terms. It's quite difficult to decide in advance that it will be high or low for the result. So we do not use exactly this expression. We are in the optical range. So this Q that you see in the, I don't know if you can read it here, it's a bit small, but here you have Q1 and Q2, that's the momentum of the photon. In the optical range, Q is very small. So in fact, this term is almost equal to 1. So it's 1 plus Q something. The 1 is gives a 0 contribution. So it means that if we use this expression, you will need an extremely precise calculation so that all the first order term in terms of Q will cancel, which is what they should do. But numerically, it can be very difficult. So what we did is to take this expression and do analytically the limit Q goes to 0, so that we do not rely on numerical cancellation of terms, which can work or not. So finally, we have this, where you see that we do not have anymore the exponential, but just the first term of the expansion in terms of Q. So that's this expression that we take, the dipole approximation of the Chi2 for numerical convenience. Of course, if you can be accurate enough in the calculation, you should recover the same result in both calculations. But then when you do the dipole approximation analytically, you have a number of terms which is huge. So this is the two first terms. Okay, so some example now. So I told you that there are some approximations. So the first approximation that we have is the Caesar approximation, because we want a good, it is important to get accurate result, to have a good value for the gap. This is very important. And this is a comparison of the effect of the Caesar approximation, not the Caesar approximation, of including a Caesar correction for the linear case and for the second harmonic. In the linear case, for silicon carbide, what you see is that you have really a rigid shift of the spectrum. The green one is the calculation without Caesar, and the red one is including a Caesar. So in fact, the spectrum is just shifted by the value of the Caesar. It's a bit more complicated for second harmonic, because in the energy denominator, you have terms that contain omega and some other contains 2 omega. So some terms are shifted by the Caesar, and some others are shifted by half of the Caesar. And so, in fact, the main effect is a mixture between the Caesar and half of the Caesar. So it's not anymore a rigid shift, and the use of the Caesar can change the shape of the spectrum, which was not really the case for the linear spectrum. Then this is now an example for gallium arsenide. Gallium arsenide is very convenient because we have very, very good experimental results. So that's really helpful when you are testing the code. That's one of the first calculations we did. So this is the independent particle with the Caesar for gallium arsenide compared to the experimental results. That's the dots. It's not awful, but it's not good. We more or less have the peak at the good position. The amplitude of the peak is we can do better. So now the next step is to do an RPA calculation. So we solve the Dyson equation without kernel, just with the effect of the Coulomb potential. And that's the blue curve. Bad luck, we're decreasing. It's very disappointing because it's solving the Dyson equation to second order is quite tough, especially calculating all the terms. It's long, it's becoming very long in terms of computer time. And then you see that when you include this term, you're going in the wrong direction. It's very disappointing, but that's life. So now we will include a kernel. And to describe the exciton. And so we used what was working very well for the linear case, which is, especially for gallium arsenide, which is the long range static kernel. So this alpha constant divided by Q square. And you see that there is a huge improvement in the result. So the influence of the exciton is for gallium arsenide in the second order case. I don't want to be more general than that. Is very, very important. So we really have the amplitude of the peak, which is good. How can we improve this agreement? Because it's not perfect. We suspect that here we have an effect of the adiabatic kernel. It could be the way to cure this discrepancy here. In this region, it could be GXE, but we do not have any way for the moment to check whether it is a GXE or not. I will show you some calculation on silicon surface. And in that case, it's the hydrogenated surface. And what we usually say from surface is that the local fields are important, or should be important, because local fields are a way to see the inhomogeneity of the materials. They reflect the inhomogeneity of the material. And when you have a surface, it's clear that you have a strong inhomogeneity. So we expect the local field to be important. And it depends on the direction of the fields. In fact, there are some cases where there are very strong local fields, and in some cases, no. So if you look at this situation, there is I don't remember which is which. The red line is without local field, so or IPA, independent particle approximation, and this one we include the local field. And it is the case where the incoming fields are perpendicular to the surface, and the polarization is detected also perpendicular to the surface, which means that we really see really the surface of the material, the below and above. And in that case, we have the feeling that there is a shift in the peak. It's not a shift. It's just a mixture of different contribution that change in amplitude. And here we have constructive interferences in the IPA case at low energy and destructive interferences at higher energy. And when we include the local field, it's the other way. And there is no shift in the spectrum. It's just some parts that are going up and down. Now, if everything is if the two incoming fields are parallel to the surface and the polarization is perpendicular, you see that in that case it's not so strong. And if everything is parallel, all the fields are parallel to the surface, there is almost no effect of the local field. Okay. And so the last example, so E-fish, it's not a fish. It's just electric field induced second harmonic. So it's the second order process plus a static field. So it's like the electro-optic effect, the Pockels effect, but to second order. So it corresponds to a process in which the two photons from the incoming field are absorbed, and a photon of energy 0 is absorbed. So it's a chi3, but the outgoing photon is the same as the one you get from a second harmonic generation. And we did this calculation because we were in collaboration with some experimental people. And they were suspecting that in their second harmonic signal, what they get was an efficient process. And it's extremely difficult to disentangle second harmonic from efficient, because if you look at the response in terms of frequency, it's a 2 omega emitted photon. If you look at the dependence in terms of the intensity of the external field, it's the square of the intensity. So it's really a mixture of the two process, and you cannot say which is which. So we decided to do the calculation. I'm not sure at that time that it was a good idea. So same business, so we write the chi3, we put one of the frequency equal to 0, so it means that we have divergences everywhere, so we have to remove the divergence because they are just fake divergence, and one term is diverging, but another one is diverging also, and they cancel, so we have to know which is cancelled with the other. And then the dipole approximation, and so we get something like this, and this is not the end. We have this also. And okay, so finally we coded these expressions without local fields. I have to admit we haven't gone so far. And this is the result of a calculation. And what is funny in this calculation is that it is the comparison with silicon and silicon carbide. Silicon carbide is a non-central symmetric material. So the chi2 is non-zero. The chi3 for efficient is very small. If you take silicon, silicon is a central symmetric material. So the chi2 is 0. So in that case, it's clear. If you get a signal, it comes from the efficient. But the final result is that for silicon, the chi3 is huge. And so I don't know whether it's a general result when you have a chi2 which is equal to 0 for central symmetry reason, whether the chi3 becomes very large. I don't know because I do not have enough experience. But from an experimental point of view, and from the idea that we can use silicon for photonics, for instance, this is quite important. And thank you for your attention.
You get a single formulation for optical. It's difficult to invent an optical amplification or something like this. You can get.
It's possible, but you really have to work hard on the expression, because when you get again for the optical frequency, optical rectification, the fact that the final frequency is 0 will induce a lot of divergence in the response that you have to remove them analytically. It's very difficult to take the result for finite frequency and go slowly to very low frequency and hope that you will get a final result. You see that at the beginning you go to low frequency and suddenly it's divergent. So you really have to do the job analytically before, otherwise get in trouble. Yeah. But once you have done this analytical limit, you have optical illusion. Yes.
Because I was just curious, how is the convergence of chi2 0 with the number of bands that you include?
It's not too bad. you have to increase, more than, in fact, usually we do first the linear calculation. We see how many bands we need. And then, of course, we have to increase because at the given incoming frequencies, you absorb 2 photons, so you need more bands because you go higher in the energy. But it is not really problematic. Just compared to the linear case, you increase a little bit, and it's not too bad. It's more difficult to converge in terms of K points. K points are important. Yes.
How many, so you showed the experimental data for the gallium arsenide. So how many experimental data are there for this?
Well, there is this spectrum, which is well, not really new. I think it is, if I remember correctly, it's 2003 or 2001, right? Beginning of 2000. For the moment, it's more or less the best. There are some, there are not so many. There are a lot of materials for which we know the static coefficient, so omega equals 0, and some points because they have a laser and they get the coefficient. So it's not always very easy to, with 3 points on a curve, to.
But it's you said for that third order, it's difficult to measure because they start destroying the material.
No, third harmonic, no, it's okay. In fact, I was told once, but by somebody who's doing experiment, that when they want to have the third harmonic, they do it in 2 steps. They first create the second harmonic, and then recombine the second harmonic with the incoming, so that they get 3. Because very often the third order process is less efficient than 2 second order process on top of each other. That's what I was told.
I'm wondering about Cockle's effect within the long wavelength approximation, because they're basically these 2 fields that are exciting the material. One is optical light, and the other one would be the static field, which has very low frequency, or basically no frequency. Is the dipole approximation actually, we're sort of like, I feel that we're reaching the limit of the model where we don't necessarily have an oscillating excitation anymore, but just a rigid shift.
In fact, the way we did it is we took the Chi2 with 2 different frequencies, omega 1, omega 2, and one of the frequency goes to 0. But at the beginning, the expression that we have is the one which is not in the dipole approximation. And when you do the limit, Q goes to 0, and one of the frequency goes to 0, you have to be extremely careful in the way you do the limit. So usually what we do is we first have the dipole approximation. So that's done, we do not have Q anymore. And then one of the frequency goes to 0. If you do it the other way, you are in trouble, because some terms are diverging. There is really a way to do it, which is, you have to be careful. But then we everything is in the dipole approximation, so the field is static, but is also does not depend on space. That's the case for the 2 fields.
I'm not extremely familiar with the formalism of the dipole approximation. At least not anymore. But Q goes to 0 means dipole approximation.
Yes.
And this would be, but if Q goes to 0, then we don't have an oscillation in space.
Yeah.
Which
we have only the oscillation in time. which is what we want.
Okay.
But we don't have an oscillation in space. In fact, it means that the oscillation in space is much larger than the unit cell, which is in the optical frequency, which is the case.
Okay. And the opposite, being away from the dipole approximation, would be using pulsed lasers or
X-ray, XUV or X-ray. But there are now experiments that are going in this direction. So the limit of the dipole approximation is not clearly really known. It seems that for many, what has been seen in many calculations, is the fact that the dipole approximation is usually valid, much more valid than what we could expect, in fact. Because there were some calculations, especially for in the case of atoms, where the two calculations were done with the dipole approximation and without. And you can go quite, in that case, you could go quite high in frequency to be still valid in the dipole approximation. But then you have also to be careful when you go away from the dipole approximation, is the fact that the order of the corrections can be of the same order of some relativistic corrections. And doing one without doing the other is problematic. And that could be a reason why the dipole approximation sometimes is valid in a very long range, just because they compensate with the relativistic correction. There's a case where we have seen that for atoms. The dipole non-relativistic calculation was very good compared to experiments. Only the keeping the non-dipole terms was wrong. Keeping only the relativistic correction was wrong. And putting the two together, they cancel, and you were going back to the dipole, non-relativistic dipole approximation. But the order of the correction is more or less the same. So be careful.